So in this part we will see Cantor's general theorem. So let's say we have set S. So for every set S, I can compile a power set of this S. What is power set of some set? All the subset of S are the element of power set of S. It is a set of subset of S. So Cantor's general theorem talks about the relationship between the cardinality of these two sets. So cardinality of a set is less than a cardinality of power set of that set. This is Cantor's general theorem statement, which is very obvious. We all know, obviously. So if in fact for a finite set we also know the exact relation. So if cardinality of S is n, cardinality of power set of S is 2 raised to n, and for every n natural number 2 raised to n is larger than n. So it seems very obvious in case of finite sets, but in case of infinite sets we have already seen some statements against our intuitions. So for example, rational number integers are equal in number, natural number and even number are equal in number. So these are the counterintuitive cases. So what will happen if my S is infinite? Still this relationship will hold. So let's try to prove this general theorem again intuitively. So I am not proving this mathematically, I am proving this intuitively. So this is my set S, which is infinite in nature, because for finite it is very obvious, and then I have some power set of S. Now you take any element from this X, S, let's say that element is X. So if I take this element X, I can surely form some other set, singleton set, which contains only X. Singleton set is the set which contains single element. So for any element over here, I can form a singleton set. So X is my in general element, so I can form a singleton set for this X. Now is this set a subset of S? So all the elements of this set are present here. So this set is a subset of S. So this X is actually a member of power set of S. So it should be somewhere here. So what I will do, for every element here there is a singleton set corresponding to that element over here. So I will map X to the singleton set containing X. Maybe there is some X1, so there should be some set, singleton set which contains X1. So X1 is mapped to set containing X1. Maybe some Xn. So there must be a singleton set containing Xn. So Xn is mapped to set containing Xn. So for all the elements over here, there is for sure there is one element over here to which I can map that element. So I will be successfully able to map all the element of S with element of PS. So for sure these numbers are not, the number of elements in S are not less than number of element in power set. Sorry, for sure these many elements are present in power set. Now the next question to probe is, in this mapping have I used all the elements of power set of S? Is there any element which remains unmapped? So let's consider a null set phi. A phi is subset of all the sets. So this phi is present in power set of S. Now all the singleton sets are mapped, and phi is not a singleton set. So phi is surely unmapped. What about set itself S? So S is subset of S. Every set is subset of itself. So S is a part of power set of S. Now again in this mapping we have only mapped the singleton set, and S is not a singleton set. So S remains unmapped. So there exist at least these two elements which remains unmapped. So all the elements in S are mapped with few of the elements in PS, but there are at least two extra elements here which are unmapped. In fact, there are many more elements which are unmapped. So all the sets which are not singleton are unmapped here. So for example, if x1 and x2 are part of this x S, then I can form a set of x1 and x2, and this is also subset of x. So this has to be here, and this will remain unmapped also. So though all the elements of set S are mapped with elements of this, so I run out of the elements in this set. I have few elements unmapped over here. So the power set contains more number of elements than our set. Even if this S is infinite, there will be some extra elements in power set which will remain unmapped. Okay, so the statement is very simple, that for any set S, its power set contains more number of elements. Its proof is also according to our intuition. Actually, this proof I have given is intuitive proof only, but it has very serious implications. So what are the implications of this statement? Okay, so the implication of statement, the first implication of this statement is about universal set. So what is universal set? A set which contains all the elements in the universe is universal set. Okay, so we represent universal set by U. So this is a set of all the elements in the universe. Okay, so if this is a set, can I form a power set of universal set? Okay, I can form power set of universal set. Now if I can form power set of universal set, what will be the relationship between these two? According to Cantor general theorem, this is the relationship between these two. The cardinality of universal set is less than cardinality of power set of universal set, which means there are some extra elements in power set of universal set. But from where these extra elements come from? Because universal set contains all the elements, and if universal set contains all the elements, there are no extra elements remaining. Then from where these extra elements come from in power set of universal set? This is a serious implication, and actually because of this implication, this Cantor set theory or naive set theory was ridiculed by a few of the mathematicians and philosophers. Cantor also knows this implication, but he chose to ignore this implication because he dedicated his entire focus on the second implication. So the first implication is this idea of universal set is somewhat problematic, because if universal set contains all the sets, all the elements, then from where these extra elements will come from? This set is larger set, power set of universal set is larger set. It contains few extra elements than this set. So from where those extra elements come from? So this is the first implication. The second implication is, again we have a natural number set which is infinite in nature. Since this is a set, I can form a power set of natural number set. Now again, according to this theorem, this is the relationship between these two. So number of natural numbers are less than number of elements in power set of natural number. Now till this point, the infinity is treated as one coherent, some abstract coherent object. What is infinity we don't know, and it is some abstract concept, but the coherent concept. Now if number of natural numbers are infinite, it doesn't have any end, how come this set has more number of elements than the infinite elements? So is there something which is beyond the infinity, and this quantity refers to that something? So at this very point, because of this implication, Cantor comes to know that the infinity is not a one single coherent object. Actually it has many layers, and that's why he gave aleph zero symbol to this infinity, because there may be some other infinities which are larger than this quantity aleph 0. Maybe I can rename, or sorry, I can name them as aleph 1 or aleph 2 if I know the relationship between them. So Cantor was more interested in exploring this second implication, so he chose to ignore the first implication and he dedicated his entire effort on the second implication. And this gives rise to degrees of infinity, because from here itself we come to know that some infinities are smaller than some other infinities. So infinity is not a single object now, it has multiple layers. So what is these layers? We will explore these layers in next part.